Right. Good afternoon, everyone. Take your seats and let's make a start. So today it's an exciting day for this course because we are basically coming to the conclusion of almost 8 weeks of build-up and hopefully interesting material. So on the screen you can see what you did over the past couple of lectures, which is Stokes' theorem, which is probably the most important result in terms of vector calculus that we've presented so far. Now, today we're going to see Gauss's theorem, or the divergence theorems, which is going to be very much in the same spirit. So that will be the first half of the lecture, roughly. The second half of the lecture, I'll try to give you a summary, a conceptual overview of what we've done in all this section of vector calculus. Okay? So I really hope that you enjoy it with me, because I find this quite beautiful. And don't worry if we are moving over or skipping over some details in terms of computations and examples, because Max tomorrow will cover a few examples to how to do all these integrals that we'll see today, mostly written in the more abstract and general form, like in that theorem, rather than going into the details of how to compute particular examples. Okay? So that was Stokes' theorem. So we're going to move to the next section on the divergence theorem. Okay, so what we're going to be looking at now is a simple three-dimensional region, E, which can be specified essentially in this box philosophy. You remember when we first started defining double integrals, we had to describe regions in some systematic way so that we could use our integration methods from single variable to compute the desired perhaps volume under the graph or area under the graph and these sort of things. So in this context, we have the same situation. When we define triple integral, we describe the regions in 3 dimensions in many different ways, but the essential sort of fundamental way of giving a description of a region for integration is by providing this sort of box description, which is essentially telling you what the faces of the enclosure is. The faces might not be just planes, might be surfaces, and in particular for this description we're giving graphs as the surfaces that will constitute the sides. So this should be familiar to you from the part of the course where we're only defining three-dimensional regions, and now we're considering a region E where this description is fitting. Okay? So we have 3 equivalent descriptions of the region with some functions that you might use to emphasize one of the 3 directions in three-dimensional space. Okay, so let's see the statement of the divergence theorem, and then we'll sketch the proof, and we'll use that particular description of the region to see how the proof will go, at least in some summary. So we have the simple region whose boundary is S, so we have an outward orientation. So very important to always keep in mind that these integration theorems carry the orientation part in them. And then we have a vector field whose components are functions with continuous partial derivatives. This will become relevant when we actually state the theorem. In that region that contains, in an open region that contains our bulk, right? So the statement is that the flux of the field through the boundary of the region is equal to the bulk integral of the divergence. So remember, this is what we saw in 2 dimensions when the last lecture I gave you, we were looking at reinterpretations of Green theorem in 2 dimensions, and one of the interpretations was that we could determine the flux, the outwards net flux of a vector field interpreted as some form of moving fluid, as precisely the line integral of the vector field times its normal. Now, if you recall the definition of surface integral for vector fields, you will recall that what we are doing essentially here with this symbol is saying that we have the scalar product of the vector field with the normal direction of the surface. So with the same sort of interpretation, this is what we interpret as the flux of a vector field of velocities of an imaginary fluid F as going through the surface S. And so if that surface is a closed surface, so it's the boundary of the simple region E that we described already, the Gauss's theorem or the divergence theorem tells us that those two quantities are the same. The outwards flux, as computed on the boundary, must equal the bulk integral of the divergence of that field. Okay, that is essentially the content of the divergence theorem. So we introduce the notation as we had for curves. Whenever our surface is closed, meaning it's the boundary of some simple region, in at least in this context, we're going to use this particular notation just to emphasize that it's a closed surface. When computing the integral, we in principle make no difference between this circle integral or not circle integral. Okay, but just to emphasize that S is, if you just see that symbol, you realize that that is a closed surface only from the notation. Okay, so let's go over the flavor of a general proof. This only will prove the divergence theorem for a region that can be described in this way, which is not the most general region. But then out of this description, you can patch for more general regions, and then the theorem can hold in more generalities, or for more general E's with more complicated boundaries as well. But for this case, let's see how it works in this case. So we have our field F that has three components, P, Q, and R. And so we know from the definition of divergence that these are just the partials. And then we have three scalars that we integrate over our region E as a triple integral, no problem. And now, if we take n as the unit normal of the vector field, if n is the normal to the surface S, then we see that this integral really means taking the dot product of that normal field with a vector field F that we're integrating. So we again get three components, or three terms rather, in our integral. Okay? We're only doing the dot product as in the definition of surface integral. So it suffices to match each of the terms. We have here the right-hand side of divergence theorem expanded out, and we have here the left-hand side of divergence theorem expanded out. So we'll show that we can actually make each term equal and can be shown to be equal. So it works essentially the same for each of the terms. So we're going to go with the third one, just for the sake of this sketch of the proof. Okay, so we're going to take the equivalent description of the region as a box with faces that emphasizes the z direction, because that's sort of the direction that we're going to be looking at. The k here, you see the k and partial with respect to z. So we're sort of focusing on the z direction. So we look at that, and we simply write down what this general geometric, as we discussed in the integration lectures, this geometric notation where we only specify this is the quantity that you compute by doing the triple integral over the region E, on the right-hand side becomes the particular expression that we're going to compute, the particular number, the particular procedure or prescription to get that geometric intrinsic number. Okay, so the way it's done is we have a projection dyx on the xy plane, and so that eventually we will compute a double integral over that plane, but the first integral that we'll compute in the z direction will involve the two cups, right? The two surfaces, the two graphs, U1 and U2 and U1, that serve as the ceiling and the floor of our region. Okay, so we notice that for this integral, these are just x and y are constants. Remember that when we perform sort of partial integrals, they are like constants, and then we have the derivative of the function that we want to integrate with respect to the variable that we're integrating over. So we can use the fundamental theorem of calculus and simply write Barrow's rule and then get this expression, right? So we're subbing in the limits of integration. You can see the top limit minus the bottom limit. Okay, no mysteries there. Now we have to perform. So this was for the triple integrals on the right-hand side of the divergence theorem. Now, looking at the surface integral, we see that we're going to have the ceiling, the floor, and potentially some vertical in the z direction surfaces being the walls somehow of this region. So in principle, we have three integrals. We have the total surface integral would be the ceiling, the floor, and the walls, right? So in principle, we have three terms. This full integral will be three terms. But now notice that the walls are, by definition in this geometric description, are parallel to the z direction. So they're normal, right? Any vector that is normal to those walls will be perpendicular to the z direction. So this projection will cancel out, and therefore those integrals that are in that particular vertical direction will not contribute to this, right? Remember that there's nothing funny going on because we're splitting our surface integral in the theorem in three, right? So each of the components will account for the ones that become parallel in this case, so that do not contribute to this particular formula. But in any case, we have the surface integrals in the ceiling and the floor. And if you remember the formula for surface integrals over graphs, so in the particular case when we are describing our surfaces as graphs of two variable functions in some perpendicular plane, we get precisely these expressions here, okay? This again is just going back to doing double integrals, and in the particular case when we describe the regions with graphs, right? So this dxy is simply the region in the xy plane where our parameters are ranging. So you can see it, instead of thinking only in three dimensions all the time, x, y, z, you can think of x, y as your external parameters, uv, that you've dealt with before when dealing parameterized surfaces. It's just that we conveniently use the geometry of the space we're working in, the same coordinates that we use to describe that very space as our parameters for integration, okay, for the description of the surface. So those two integrals are oriented that way. This minus sign obviously comes from the fact that one normal direction will be pointing downwards and the other will be pointing upwards, so one of them will have a negative component in that z direction. And then we clearly see that this integral minus that integral is precisely what we had before, is this integral minus that integral. Okay, so the same will go for each of the other two components, and therefore we have a divergence theorem, which statement is here. Okay. Any quick questions about the sketch of the proof? Again, the stress of today's lecture is not so much the technical details of this proof, it's more getting the idea behind the statement. So in order to get a first feeling of how this might work in practice, let's go over this example. So imagine that we're asked that we're given this vector field f, which looks horribly complicated at first to manipulate. I mean, we have some exponentials and trigonometric functions. It looks fairly complicated to work with at first, especially if you wanted to, for example, integrate it, right? Remember that integrating, even if we are doing, surface integral and double integrals and so on, at the end of the day, you're going to be computing some single variable integrals, right? So all these functions are looking pretty scary to integrate. So now, instead of just going straight on and trying to compute that integral, which would be, or potentially could be quite formidable, we're going to use the divergence theorem to find an appropriate bulk region that is enclosed by the surface S, and therefore just compute the integral inside of that region. So S is the surface of the three-dimensional region E, bounded, and now we basically give a description of several geometric objects in R3 to describe how we're bounding our region. So remember, S is going to be defined as the boundary of some three-dimensional region, and then all the prescription that comes after this point, bounded by, they're just all the necessary data that we require to describe a region in R3. So notice that we have a parabolic cylinder. So this is essentially z equals 1 minus x is a parabola in the zx plane, and so we can sort of project it, and we have a three-dimensional sort of dome in x, y, z space, and then we have the plane z equals 0, we have the plane y equals 0, we have another plane that is sort of tilted with respect to these, and then we're saying that is the region that we're enclosing. So we're not going to spend the time to actually draw everything, because it will take some time, but you're probably already familiar with this sort of procedures. From the very first time we talked about this, I said most of the time when integrating, at least in this course, you're going to spend a lot of time just going over the description of the region more than the actual integration, as you're familiar with. Okay, so before we describe the region, we're going to think, okay, actually, I want to employ or apply, rather, the divergence theorem. And instead of computing a surface integral, I will compute a bulk integral. So for that, if we go back to divergence theorem, you realize that you have to compute the divergence of the field, hence the name, easy to remember. And so we indeed compute the divergence, and then we see some really nice things happening, right? Because the partials of the components of the vector field simplify a lot, essentially because there's no dependence of the appropriate coordinate in the appropriate place. Okay, this is just an accident, but it was so to make a point that by using these integration theorems, things might become a lot easier than it might seem. And they might seem. Okay, so we just get a very, very simple expression, 3y, a linear function, super simple function to integrate over a bulk. Now the next part of the exercise will be to describe the bulk. And this is an exercise in geometry. Again, I will not cover the details here, but you can see after some drawing and after some careful consideration of ranges of the three independent variables, that is the region that you need to integrate over. So again, we have a box description of our region, right? We give a range for x, we give then a ceiling, a floor and a ceiling for z, and then we give again some walls for y as well. Okay? So from this point, we simply apply divergence theorem, right? So we start with a surface integral that we want to compute. We turn it into a triple integral with the divergence. We insert the divergence that we computed, and then now we have a triple integral with a function. We can forget about the context of the problem, and from that point, if we are sure that what we did to this point was correct, all you have to do is a triple integral that I'm sure you've practiced a lot already, and you should be getting quite swift with. So, two integrals iterated. Remember to keep the order of integration as with the description of the boundaries, and everything should follow through quite simply, and then you get a number, which is the value of that integral. Okay? Any particular questions when it comes to this example? I think it's quite straightforward. Okay, so this is the end of the slides, and for the rest of the lecture, let me see. Okay, perfect. I want to make a summary, a big summary of what's happened so far in the vector calculus section of the course. So let me begin by, so remember that I told you this funny story about how we have our so we can think of vector calculus as a matter of show or movie where we have our stage or our setting and we have our characters and our plot lines, right? So we're going to have, okay, so let me see. So when we're thinking in R3, right, in 3 dimensions, we have 4 kind of objects that have come up in the course so far and that enter the statements of the theorems that we've given you. So we're going to think of their dimension. Let me get the spacing right. Okay, so this is going to be 0. It's going to be 1. It's going to be, okay, let me, where's mine? Okay, 0, right? Let me space them properly. So let's go dimension 0 here, dimension 1 here. Okay, so let me say here maybe shape. And I hope this diagram will start to make sense as I draw it, don't worry. So what is dimension 0? Okay, dimension 0 objects are points in my space, right? So things that we visually identify as like little dots, okay? We can give them some generic names, x, y, etc. Right? One-dimensional objects are curves in our course, okay? So it might be a curve with some endpoints, or it might be some closed curve. Right? These kind of objects. Dimension 2 objects are surfaces, okay? Some surface with a boundary, or maybe some closed boundaryless surface. Okay. And then 3-dimensional objects are bulks. They are volumes in our space. It could be the whole space, that's a potential 3-dimensional object. It could be just 3-dimensional subregions. So, for example, it could be a bulk this way, you know, and so there could be a bulk, I don't know, with a different shape, you know, whatever it's inside. Okay. Now, go back to your notes or the memory you have from the lecture on vector fields and operators of vector fields, and when we introduced gradient as an operator, and we introduced divergence, and when we introduced curl. And remember that the two main sort of actors in our show are functions and vector fields. Right? These are the two main objects that we're going to be dealing with. And so actually, there is a natural way to sort of identify functions and vector fields with these shapes that I drew on the blackboard. So remember that, so as a reminder here, functions, I will use this brief sort of shortcut notation for functions. So these are all the functions of this form. And remember that we'll require of them the sufficient differentiability property so that we can write the statements that we will. And then also the vector fields, so curly V for vector fields, which are maps of this form that send triples of real numbers to triples of real numbers, because obviously we're thinking of the concept of assigning a coordinate point, x, y, z, to a component, to a set of three components, right? Fx, Fy, and Fz. Okay, again, requiring the differentiability properties that might be necessary, so the statement makes sense. Right. So in the field, sort of row, we're gonna be thinking of, okay, if I have points, what is natural for a point is to say I have a real value here, right? So the object that we're going to be attributing to points are functions, right? These are sort of the algebraic version of a point. Now, what about curves? Curves have tangent vectors, right? There's vectors that go along these tangent curves. So somehow, at least locally, we can identify curves with their tangent vectors. So we're going to think of the field object or algebraic object corresponding to curves as vector fields. Similarly with surfaces. If I give you a vector field, you can think of the normal to the surface at every point. And so at least locally, you can think that the surface is being characterized by the little vector. So maybe let me emphasize that by writing some tangent vectors here. Right. And by writing some normal vectors here. Okay? So that's why I also attribute the field equivalent to surfaces as vector fields. And then finally, if I have a bulk, again, we are in the setting where we just have some region and we attribute some value to the region, like when we introduce functions as a basic concept, right? So again, we're going to think of functions as being the appropriate algebraic equivalent of a bulk. Okay, so this might seem fairly abstract and you know, a bit pointless at this point, but remember what operators we had a few lectures ago that allow us to jump between these states. So remember that we have gradient, right, that took functions and gave us vector fields. Remember that we had curl that took vector fields and gave vector fields, and we had divergence that took vector fields and gave functions. Okay? So if anything, I mean, this diagram is trying to summarize that overall algebraic structure that we discussed in the lecture on differential operators on functions and vector fields. Okay? So the sort of relation between shapes of fixed dimension and functions and vector fields at this point is purely analogous. I'm just saying keep them sort of ordered this way in a chart so that I can push the organization of information further and make things visually clear when I write it on the blackboard. Okay. So maybe some of you have noticed something about the fact that we have 4 sort of dimensions for our objects, and therefore 3 jumps in dimension, from 0 to 1, from 1 to 2, and from 2 to 3. There's the same number of jumps in dimension as there are differential operators between our fields. Okay, that at first you might think, oh yeah, that's just an accident. There's nothing deep going on there. Actually, there's something deep going on there. So we're going to see that manifest in the number of integration theorems. How many integration theorems have we given you? You might be thinking, actually, many of them, because Green's theorem has several versions, and then Stokes' theorem, Divergence Theorem, the conservative field theorem, and all these kind of things. But actually, we've essentially only given you 3 different integration theorems, and then we're going to see them manifest in this way. So imagine, so let me draw some vertical lines. So there is a interface of dimension here, okay? Let's see if this works. I'm going to try and do a diagram that crosses over 2 blackboards. I don't know if it's going to work. I hope it does. Okay, so we have this division here. We have this division here. Okay? So this represents, wait, I think I wanted to do, sorry about this. I want to do the jumps in dimension, not cut the dimensions in half. Okay. So I want to have one for the jump between 0 and 1, right? I want this jump in dimension. So I'm going to draw a line here. I'm going to do the jump in dimension from 1 to 2. So I'm going to draw a line here. And I'm going to have the jump in dimension from 2 to 3. Okay, so I'm going to have this other side over there. Okay. So the division will be somewhere here. The division will be somewhere here. Okay. So now this is going to be our integration theorem. Rho. Okay. We're going to see integration theorems in this direction. So you perhaps remember this geometric situation, okay? When we have a curve oriented in a particular direction, we call C, and we have some endpoints, okay? We call X and Y. So we are in the interface 0 to 1. We have a one-dimensional object, the curve, that has boundary, a zero-dimensional object, which is a collection of points. Okay? So let me state a theorem that you might recall from earlier lectures, which is if I write the integral over my curve, use the colors in a convenient notational way, of some gradient of a function, right? I mean, you might want to use the vector notation here. Then, remember that essentially the fundamental theorem of calculus for functions of several variables was stated so that the value of a line integral of a gradient vector field basically amounts to taking the values at the endpoints, right? So what this is evaluate your function at the starting point with a minus sign, and then the function at the endpoint. So f at x with a minus sign and f at y. Okay? Does everyone recognize this theorem from before, right? Good. Okay. Let's now go to this jump in dimension. So we are in dimension 1 to dimension 2. So if we have a two-dimensional object, its boundary is going to be one-dimensional. Okay? So let's see. Kind of picture I want to draw is I have something like this. right? S. And it has a boundary. So okay, something like this. Now, I want things to have some orientation. So this thing is going to be oriented in that direction, and this thing is going to have some outwards normal. And this is what we call the plus normal direction. Okay, so we choose an orientation for both objects. This object is oriented. Okay, by the way, the orientation here is minus and plus, so that reflects over here. Just as a reminder. I mean, this is the theorem, and this is sort of the picture, but we're trying to put things together. Okay, now, remember Stokes' theorem. What does Stokes' theorem tell us? Well, we have a double integral, a surface integral that becomes a line integral. So if we compute the double integral, of a curl, a vector field, over our region, or a surface, sorry, S, what we get is the line integral along the boundary. So now this is, a boundary is always closed, so we emphasize that with the circle, and then we do the line integral over the boundary. Okay? Everyone happy? This is just Stokes' theorem again. Very good. So let's jump in dimension from 2 to 3, right? Let's see what happens. So this is kind of trickier to draw because we obviously live in 3 dimensions. So we all will have to take a trip to the 4th dimension to actually visualize this properly, but fortunately we can do that. So let's try and make sense of this. So my boundary, I'm going to draw the boundary first. My boundary is going to be some bulk like this. Is the shell of this bulk. This is S. And then what's inside is E, right? So E is whatever is inside. Okay? So what do we have? We have divergence theorem, we just saw it today. So we have triple integral over E of some field F, and this becomes, by divergence theorem or Gauss's theorem, it becomes a surface integral that is always closed because we are the boundary of something along the boundary S of simply that field. Okay? How are we doing with time? Okay, that's good. Right. Everyone happy with this? This is just a summary. So let me just write down the names that you are familiar with. So this is called fundamental theorem of calculus in R3. This is Stokes' theorem. And this is Gauss's theorem. Okay. So I hope that you can see from my diagram spanning 2 blackboards that these 3 theorems that you've seen in different contexts and with different sort of flavors really connect with this basic exposition of differential operators and dimensions of different shapes in R3. So you see you have as many fundamental integration theorems as you have jumps in dimension. Okay, I'm going to repeat this again. I know it's quite clear from the blackboard, but let me just go over it again. We have 0-dimensional objects as points. We have 1-dimensional objects as curves. Then fundamental theorem of calculus in this context relates an integral of the corresponding differential operator for that jump of dimension, which is gradient, and an evaluation of a function, right? So we have that way of connecting a one-dimensional integral with a zero-dimensional integral, which is really just evaluating the function at the point. Now, when we have a surface that we have 2 dimensions and it has potentially some boundary that is one-dimensional, we have the differential operator that corresponds to that jump in dimension, curl, and we have the theorem that goes with it. So that is Stokes' theorem. And we see how we transform a 2-dimensional integral into a 1-dimensional integral. Okay? And then finally, we see if we have a 3-dimensional object E with some boundary that is now 2-dimensional, we get that through the differential operator divergence, we relate a 3-dimensional integral, a triple integral, volume integral, with an integral over a surface. Okay? So in some sense, the same way that when you were in your, in high school and everything is simple and nice, and just functions and derivatives and integrals, everything sort of falling into place, all the problem is how do I actually compute this more than where are things going, where are they living, where are they moving. Now we have promoted, we're grown-ups, we're now dealing with several dimensions, and the basic idea that integrals and derivatives are sort of inverse operations of each other, and that you can differentiate something, then integrate it and get back the same thing, and vice versa, is really manifest in this. So when we promote to a higher dimensional space, now we have 3 dimensions, 3 full dimensions, realistically, we are rendering space as we experience it. Now, that basic idea that differentiation and integration are sort of inverse operations of each other is manifest in this structure. Okay? The idea that there's a single notion of integral and a single notion of derivative, and that they are inverse of each other in some sense, it's really only a case for, it's only really the case for one dimension, right? Or dimension 1, just for R. Now, when we are in R3 in 3 dimensions, that concept, that intuition, becomes this full statement, that for each jump in dimension, you get a sort of integration theorem and a fundamental theorem of calculus for that jump. Okay. Some questions, some general questions about this, because we can push this a bit further and make this into a 3 blackboard diagram and make a few more comments. But this is the core of what we wanted to emphasize today, right? We really wanted to sort of ingrain in your mind that there's these 3 jumps in dimension, and that's how you compute. That's how you relate. Not so much how you compute. That is a matter of describing the regions and so on, things that you will get practice. Max will go over examples, both Stokes' and Gauss's theorem again tomorrow, so don't worry about this. It's more important that you get the basic idea of what we're doing here. Some general questions about this before I make a few extra remarks. Okay, so thanks to this more pictorial, perhaps, understanding of, okay, so I'm going to get rid of this blackboard for today. Goodbye. And okay, so thanks to this, we can say a few things about integrals more generally. Okay, so we can say, for example, just by recalling the picture, I really want you to remember. I mean, I know that the statements of the theorems, the first time you see them, they look kind of convoluted and a bit messy, and there's a lot of symbols, and things are very packed. Whenever you write a double integral over a surface, there's a lot of information to unpack, right? There's a lot of, I mean, you'll need a parameterization, you will need to compute the normal and the cross product of the partials. It's kind of, there's a lot of information. It's very heavy notation. But imagine that you've mastered all that and you've gained enough practice to actually compute confidently with these things. Now, these are quantities that you can compute of surfaces or regions and fields, functions or vector fields. So I think it's very important to keep these kind of pictures in mind, because you can conclude things that are not simply the statements of the theorems. The statement of the theorem is really telling you, okay, relate these 2 integrals, relate these 2 integrals, and relate those 2 integrals. But actually you can conclude more things, and you can say things that at first might not seem direct consequences of those theorems, but they actually are. So let me continue the diagram. Okay, we're doing fine in time. And okay. So just a reminder how to read this diagram. Up there we have the four different dimensionalities of objects in 3D, and then these 3 bands of the diagram are jumps in dimension. okay, which you can very much interpret like this pictures. One-dimensional object has, if any, zero-dimensional object has boundary. Two-dimensional object has, if any, a one-dimensional boundary, and three-dimensional object has, if any, two-dimensional boundary. Okay, so this is terribly tilted, sorry. Okay, so things we can say about vector fields and integrals. Okay, so for example, if I give you 2 points, x and y, and I give you a vector field, so this is very much the question of conservative vector fields. Okay, so let me write it here. Yeah, conservative. And this is kind of a joke. I mean, this is the quality of being conservative. This is about, well, let's feel it later. Okay, so if I give you a vector field f and 2 points in R3, then I might ask you, okay, what is the line integral over this curve? You say, well, actually, if f is precisely the gradient of a function, then all you have to do is evaluate that function at the endpoints, right? So basically, when f equals nabla of some function, actually let me call this g. When I have this kind of situation, I find the integral of f to be only determined by the endpoints. So what that means is if I take, so this is c, if I take a different root, call it c prime, this equals in particular c prime FDR, which is precisely this idea of path-independent functions, right? And indeed, any other complicated path that you can imagine, as long as it's differentiable and it satisfies the conditions that we imposed, that we assumed in the theorem, it should be the same, right? So this is a very important consequence of this theorem. The fact that we can relate things that way is that when we have a field that is a gradient, might be a gradient in disguise, right? It's not, might not be given you as a gradient, might be given you by some expression, but actually you can show that it's a gradient of something, then suddenly the integral, the line integral of that field does not depend at all on the path you take. So that could simplify your life immensely, because doing those integrals might be very difficult, but if you take a straight line between them, maybe that integral is super easy to do, because you're just computing over a line. Okay, all those integrals will have the same value, non-zero, the same value. Now, obviously, if you have a function that has zero gradient, right? So when you have a function with zero gradient, and clearly this thing here always vanishes for any curve, right? So what I'm saying is that according to the theorem, the value at x plus the value at y will equal the line integral over c, for c, any curve joining them. But the gradient is zero, I'm assuming that. So this is necessarily zero, right? I'm integrating the zero vector field over the line, so obviously I get zero. So what this is telling me is that f of x equals f of y. So what that's telling me is that for all the points that I can connect with a path, the value of the function is constant. Right? This is what we call a local constant. Something that, as long as we can connect two paths, the function is constant. If the function is defined everywhere, this is just a global constant. It's just a constant over R3. Okay? So this is a way to actually show that this idea that a constant in single variables, back in high school, a constant in single variables has derivative equals zero. Right? So now we can make that statement very precise in this multidimensional setting by saying, well, if my gradient is zero, I can use this theorem to connect these 2 points and then realize that their value is the same. Okay? Very good. Let's go to the next jump in dimension, and let's talk about similar things. So what kind of picture do I want to draw? Imagine that I'm going to simplify the wiggliness of my drawings to make my life a bit easier. Okay, so imagine that this is my boundary, C, and imagine that I have some vector field, F. A vector field in R3, okay? Now, imagine that I'm interested in this integral, right? I want to compute the line integral of this vector field. This is in principle a general situation that you've done several exercises of already. So one thing I know is that when that vector field is exactly curl of some other vector field, right? This is not always the case, but when that is the case, then I know that this side of the theorem is always the same value, right? Sorry, what am I saying? Sorry, my bad. Forget the last 2 minutes of what I said. Let's think of this surface. Yes. Okay, so, okay. I don't have to forget too much of what I said. Imagine that I want to compute a surface integral. So I want to compute this surface integral. Okay? So, according to Stokes' theorem, when my field is the curl of some other field, I can express that as the integral over the boundary C, right? So in particular, if I change my surface, I make my surface, for example, this thing. These are two different surfaces, right? Or make my surface this other thing, or indeed just the disk. And here, all these different surfaces, S prime, disk, S prime prime, whatever. All these different surfaces, they will all have the same value. Prime, FVS equals, etc. Right? All these surfaces will give me the same integral over the field. So we have a very similar situation to what we had here. I have potentially a very complicated integral if I complicate my surface a lot. But if this is the case, when my field is the curl of something, then we can simplify it, and actually it doesn't matter which surface you choose. Right? So it's not only that you can compute it with a line integral, which you can, according to the Stokes' theorem, but is that the integral has the same value regardless of which surface you choose. Right? So that's two ways of reading these kind of theorems. That, yeah, we can transform the sort of the dimensionality of the region we're integrating over, or under some conditions, we see that it doesn't matter which region we choose, as long as they all share the boundary, okay, for the value of the integral. Now, similarly to this description, when when the curl vanishes, so what happens when the curl vanishes? So what happens when the curl vanishes is that this right-hand side is always 0, right? So that means that I can always relate, if I have, imagine, two curves that look like this, so that I can enclose them as sort of this cylinder, right? I can enclose them as being the boundary. So this would be some orientation like this, right? If I have C1, C2 in this situation where I can enclose them by a surface S, whose boundary are precisely these two curves, then I'm assuming this is 0, so I'm assuming this right-hand side is 0, so the integral over the boundary will be 0. Now remember, the boundary will be like, very much like in this case. I have integral over this, of f plus, well, minus this because it has opposite orientation, so happens to be equal to this one. Okay? Right, so that's us done with, I mean, if you're wondering about this jump, we have a similar theorem when, I'll let you think about it a little bit if you want, when your field has no divergence, then obviously it doesn't matter which shell you choose to compute the outwards flow, it's never flowing out because it has no divergence. So we get a similar theorem, but now for different shells. Okay, thank you.